Our mission today is to build a step-by-step guide to the inner workings of linear regression models.
Which sounds intimidating, but I mean, drawing a line of best fit through data is a concept you're probably already familiar with.
Exactly, but the real question is, how do you know if that line is actually telling you the truth?
Well, a line on a graph doesn't really prove anything on its own.
No, of course not.
Right, because it is incredibly easy to just force a straight line onto a data set where it doesn't belong at all.
So to prove a model is sound, you have to run it through, well, specific statistical lie detectors.
I like that term, yes, statistical lie detectors.
So let's start with step one from those textbook excerpts, which is interrogating the errors.
Right, before testing whether any specific variables actually matter, you have to verify the model's structural foundation.
And paradoxically, you do that by looking closely at exactly what the model got wrong.
Yeah, the residuals. I mean, these are the vertical gaps between your actual observed data points and the predictions your model made on the line.
So for a linear regression to be valid, the underlying math assumes these error terms are uh, independent.
Independent, normally distributed, they have to have a mean of 0, and they possess constant variance.
Okay, hold on, wait. Those are a lot of textbook rules thrown at us all at once. Let's ground this a bit.
Sure.
If I picture throwing darts at a dartboard while blindfolded,
Okay, I'm picturing it.
a fundamentally sound model means my misses, right, the residuals, they should look like a completely random, patternless scatter around the bullseye.
Which represents our 0 line.
Exactly.
The blindfolded dart throw is a really helpful mental model, actually. But consider what happens if your throws aren't just a random cloud.
Like if I'm not just terrible at darts.
Right, what if, say, all your misses are heavily clustered in the top left corner of the board?
Well, that would mean I'm not just bad at aiming. There must be, I don't know, a massive gust of wind hitting the board that I completely failed to account for.
Exactly. And that gust of wind is an uncaptured pattern in your data.
I see.
Yeah, when you plot your residuals and they start to form recognizable shapes, it means your model is missing something fundamental.
And the slides highlight a couple of specific visual warning signs for this, right? Like a widening funnel shape.
The funnel, yes. Or double bow.
A double bow. That's where the spread of the data widens out and then pinches back together.
Right, and seeing those shapes means your variance is actively changing across the data.
Which breaks that rule from earlier.
Exactly. The assumption of constant variance is broken. I mean, if the
Yeah.
model can't even maintain a consistent level of error, it is structurally inadequate.
So any predictions you make with it are essentially built on quicksand.
Exactly.
So let's say our residual dartboard is perfectly random.
Okay, a nice random scatter.
No funnels, no unseen gusts of wind. The foundation is solid rock. That creates a natural bridge to the next step of our guide.
Right, because now that we trust the model as a whole, how do we prove that a specific variable inside it is actually doing any heavy lifting?
We interrogate the individual parameters, like the slope of the line.
Yes, using a t-test. You always start with a null hypothesis.
Null meaning nothing.
Right. In plain terms, the null hypothesis claims your regression coefficient is exactly 0.
Meaning the variable you are testing has absolutely no linear relationship to the outcome.
It is just meaningless noise.
So the alternative hypothesis, naturally, claims the coefficient is not 0.
Exactly. But testing this in the slides involves computing a test statistic.
Right, by dividing the estimated coefficient by its standard error. Let's pause there for a second. Why standard error?
Yeah.
What does that division actually tell us conceptually?
It is basically a calculation of signal versus noise.
Oh, I see.
Yeah, your estimated coefficient is the signal you found in the data. The standard error is the background noise.
So by dividing the signal by the noise, you are checking if your finding is loud enough to be real.
Yes. If the resulting number is large, it means your signal overpowers the noise.
And that translates to a p-value dropping below 0.05, which leads you to reject the null hypothesis.
Right.
But I have to point out the irony of this terminology for you, the listener.
The wording is pretty counterintuitive.
Yeah, rejecting the null sounds like a failure.
Like you did something wrong.
Right. But mathematically, it's the exact victory you want. You're proving your variable is actually significant.
You are actively defeating the assumption that your variable is useless. Getting the mathematical green light to reject the null is the entire point of running the test.
Wow, we've guided you through quite a journey today. I mean, we started by validating your model's integrity.
Hunting for funnels and the residuals.
Right, to ensure a solid foundation.
Yeah.
And then we moved all the way to proving your variables actually matter by weighing signal against noise.
The rigor behind these models is really intense. It's never just about drawing a line.
No, it's about proving the line actually deserves to be there.
Absolutely.
But to leave you with something to chew on, we talked about how a funnel or a double bow breaks the constant variance rule.
Right. Bad shapes.
But what if you plot your residuals and instead of a random scatter, you see a distinct, perfectly nonlinear curve?
Oh, well, a clear curve in your errors implies your data is operating under a completely different mathematical reality.
A reality that a straight line of best fit can never actually capture.
Right.
It turns out your statistical lie detector might just be telling you that you've been asking the wrong question all along.